Okay, and so hello everyone, welcome back to Global Kids Mathematics. So last class we couldn't follow our usual schedule due to my timing kind of problems with my flight coming to the US, and so this Saturday we'll be covering a Thursday topic on polynomials, and I did send an email regarding the change schedule as you thankfully currently came in the right time. It's been delayed by 2 hours from our original class times, and also the schedule has been pushed back by one time slot as well. And so, with that kind of small note out of the way, I think we can go into our topic of today, which is polynomials. And so, just before we get into our topic, our specific concepts, uh, we covered a lot of other topics that utilize a lot of polynomials, whether that be rational functions, quadratics, or linear equations. And so, uh, there might be topics that you are kind of familiar with and kind of already understand how to do and how to solve questions. But there's also a couple new concepts, and so it might be a bit lighter in terms of the kind of material that we'll be covering today. And so, but still, it's still a very important part as there are slight details that we haven't covered yet. And so we'll be covering those today. And so moving on to our first concept of today will be simplifying polynomial expressions. And so what this means is basically just, as it says, polynomials are expressed with variables, coefficients, and non-negative integer components combined using addition, subtraction, and multiplication. Actually, I might change the definition to get rid of the non-negative integer, excuse me, exponents. In terms of exponents, yes, most of the polynomials that the digital SAT covers, especially a long series of polynomials with multiple degrees of exponents, usually are positive and non, or also so called non-negative. And so it'll be very rare and almost I can't be 100% sure, but I am pretty sure that negative integer exponents probably won't be on the digital SAT. And so we're basically just combining such polynomials using addition, subtraction, and multiplication. And some key skills is to simplify by combining like terms and dividing terms with common factors. And so we'll take a look at some example questions and how they can be solved. And so the first question states, which of the following is a solution to the polynomial equation below? And so we are given a polynomial equation as such here, and we are also given four different answer choices. And so there are multiple ways to solve this one. Uh, so first one would be trying just to plug in each answer choice into the equation itself, seeing whether it will might be a solution. Uh, that's a valid solution and a valid method, but then there are more, I guess, other mathematical concepts that could be utilized. And so we'll talk about this in the later slides as well, but then I think it's good to cover it now. And so we'll be covering something. So when you're given a polynomial with a high degree exponent, for this one being 3, and so it might be difficult to kind of try to factor this one because until quadratic functions, so polynomials with the max highest degree of 2. We were kind of used to, and we were able to factor them out just by kind of trial and error. But then for third degree, it's a lot more difficult. And so we'll be utilizing a method called, excuse me, let me just go to a later slide, just talk, uh, what was it called? The rational root theorem, as we will see in later slides. And so the rational root theorem basically means uh, kind of is a method to solve high degree polynomials without just the original factoring method that we used to. And so I'll run through how we can utilize that. And so first of all, when we are given a polynomial as such, the first thing we have to do is to rewrite it so that on one side we have every value and every variable, and on the other side it is equal to 0. And so we can change that by just moving this -5 over so that we get 3x to the power of 3 minus 2x squared minus 14x plus 4 equals 0. And so once we have this form of the polynomial, uh, we now utilize the rational root theorem. And so just to show an example of how we do it, so the first method is to uh, just write down each coefficient of each variable. And so we first write down the coefficient 3 of the variable of x to the power 3, and then -2, and then -14, and then +4, so that we just write the coefficients exactly as they are. And then we draw kind of a somewhat you might be used to like an upside down division symbol. So when we're usually dividing some kind of either number or polynomials, we kind of flip that around. And then from here, uh, you would usually plug in any single integer or fraction or just any kind of a constant value into here. And so for our example, I will utilize uh, okay, let's try just the constant 1. And so if we do constant 1, so how you do the rational root theorem is that, first of all, the first coefficient we have, we just drop it down as it is. So it will just be 3 down here. And then from here, for each value that is below the this line, we multiply by the constant we wrote on the left-hand side. And so we multiply. That will give us 1 times 3 is just 3. And so we write 3 again, but then on the second level. And then from here, so we multiply with the constant when the number is below the line. But then when the number is above the line, we add these two values together. So this is a addition. And so if we add those two, then we get -2 plus 3, which is just +1. And so again, below the line, we multiply by the constant. And so 1 times 1 will just be 1. And then again, we add so that we get -13. We multiply again so that we rewrite -13. And then we add again to get -9. And so what this kind of method is talking about. So right now you might be confused as though, okay, we did this, but what does this mean mathematically? So this is another method of kind of dividing a polynomial by another linear equation. And so what this means is that this entire, I guess, function or theorem or method that we utilized is basically just dividing this, our original polynomial, by x minus 1. And so the one that we put in as the constant on the left-hand side, you can kind of think of it as being the same as just plugging a value of 1 right into the polynomial itself. But then the reason this method is useful is that we can know that for whatever linear equation we divide it by, this will be the remainder. The final value will be the remainder, and this value will be the other divided constant. And so what I mean by that is if we divide our original polynomial by x minus 1, then we get this value with a remainder of -9. And so this is why this method and this rational root theorem is very useful within mathematics. But then for the sake of our question, we needed to kind of factor it out. And so we needed to find a linear equation that we can divide by so that we get a remainder of 0. But we couldn't get a remainder of 0 with a constant value of 1. And so we'll try again. And so this method also kind of requires you to utilize some trial and error to find the correct answer. And so, but a tip is that if we use the constant 1, we got a remainder of -9. And so we kind of divide it by, one moment. Yeah, so if we use 1, then it was a value that was too large, and that's why we got a remainder that is a negative value. And so, a key thing to note is that if you got a remainder that is a negative value, you usually, or almost always, want to decrease the constant on the left side here. And so just to kind of tell you the answer and go through our problem, if we plug in a -2 as our constant of division, then again, we drop down to 3. We multiply with -2 so that we get -6 here. And then we add so that we get -8. And then again, we multiply by -2 so that we get +16. If we add -14 and +16, we get 2. We multiply again by -2, we get -4. And once we add the final step, then we get a remainder of 0. So once we get a remainder of 0, what this means is that we can divide our original polynomial up here by the linear equation x plus 2. Remember, it has to be plus 2 because this -2 represents the value we have to plug in for x so that we get a 0 value. And so if we divide by x plus 2, then we get a kind of simplified polynomial of 3x to the power of 2 minus 8x plus 2. And so we can say that we divided the original polynomial by x plus 2, or we can also say that we factored the original polynomial so that it is x plus 2 times 3x squared minus 8x plus 2. And so uh, through this method, we kind of found how we could first factor a higher degree polynomial. And so from here, you can see that uh, -2 is a solution that is a answer choice here. And so our answer will be B. But then we can further check the second the remaining quadratic function to see if that also has a solution that is listed within our answer choice. If we were to do that, uh, so you can kind of utilize, if you remember our previous topics and our previous class, the quadratic function, and so or the quadratic solution formula. And so if we just quickly utilize that, and if we check the determinant to see how many solutions there are, then first of all, if you remember, the determinant was if we just ignore the root for now, it was b squared, and so -8 squared. So I'll write determinant is equal to -8 squared minus 4 times a times c, so a being 3, c being 2. And so if we calculate this value, we get a value of 64 minus 24, which is equal to 40. And so it's greater than 0, and so there will be two solutions. And so let's try to find the solutions. And so the solutions, the remaining other solutions other than x equals -2, we can find by the quadratic formula for this quadratic function. And so if we were to do that, then we get -b being +8 plus minus root. If you remember, we got a determinant value of 40 with inside the root. And so that'll be over just 8, so 3. And so right away, we can kind of slightly tell that even if we simplified the root, and so we change it to this form, this root 10 is kind of blocks us from having a constant solution, and it's also a solution that is not written in any of our other answer choices. And so the only answer choice that could work for our case is answer choice B. And so anybody have any questions for this one? Uh, okay, I seem Streaker has a question, but I'm very sorry. The For some reason I just can't seem to hear you through your microphone. I apologize, Shrikar, but this does seem to be a problem with your microphone, maybe. If you have a question, you can leave it in the chat.
Can you hear me now, sir?
Oh, yeah, yes, I can hear you. Okay, that's great. Okay, so does anybody have any questions regarding this problem? Okay, seems like not. It seems like everybody did understand the rational root theorem or this method that we utilize. Oh, sorry. And so I think we can move on. And so, yeah, uh, actually, the kind of most important concept that we had to cover was the rational root theorem and how to utilize it when solving problems. And so that was great. Sorry, solution might be incorrect. We'll just move on. And so we move on to our second practice question, which talks about which of the following is not a correct solution to the following polynomial function fx is equal to 0 of the following polynomial equation. And so the question says when fx is equal to 0, and so when this kind of complex polynomial is equal to 0, we need to find a uh, solution that is not a correct solution. So one of these four answer choices will be incorrect in their answer choice when being a solution to our polynomials. And so first we have to factor out everything and just try. Uh, you could also, like I just talked about in our first question, just plug in each answer choice value in place of x and check if that works. That is possible. In some cases, that might be quicker, but then we'll also cover on how to factor these functions. And so first of all, let's try to factor out the polynomial with the degree of 3 using our rational root theorem that we just used. And so again, uh, so this time we're not doing the full equation, but just only part of it. When we're doing just a part of it, just think of it as we're factoring only this. And we'll think of that as being equal to 0. And so if we use the rational root theorem, again, we just write down the coefficients of each value down, and then we draw this table. And so from here, we kind of plug in a value that could work here. And so I usually just always start with either just -1, 0, or 1. For our case, 0 will not work because that will just be factoring by just x, which in our case, we have a constant, and so that will not work. And so we'll try either -1 or 1. But just for simplicity, we'll just try the constant 1. And so if we were to try constant 1, then if we do the method that we always did, then we'll get a value of -16. And so again, if we got a remainder or a value here that is less than 0, then it means our original constant that we divided by was too big. And so we'll lower it down. Let's try -1. We tried -1. Uh, a bit smaller value, -5, but still it is slightly too big. And so we'll lower the value by again by another uh, 1 so that we get, let's try -2. And so if we were to try -2, oops, excuse me, then we will get 1, -2, -4, +8, +2, -4. Oh, sorry, I think I made a mistake somewhere. Hmm. Okay, -12. How did this happen? Let me just rethink. Okay, okay, seems that -2 also gets us actually a smaller value than when we did -1. And so another thing I want to talk about is that if we used a constant and so we got a -5 remainder when we used -1 as our constant. But if we were to do that, and then we changed it to -2 and got an even smaller uh, remainder of -12, which means that the solution will be greater than -12, but less than 1. And so, or excuse me, less than -1. And so we can maybe try for our final try. Uh, excuse me. Uh, so yes, we try -2 and -1. It needed to be smaller than -1, but it also need to be bigger than -2. And so maybe we'll try -1.5 or also the fraction -3/2. So if we try the fraction -3/2, uh, excuse me, that also probably won't work because our first coefficient being 1 will make it a lot more complex. And so, hmm, okay. And so another method, if going down or going up the values does not work, is if you look at the constant or the last constant or the last coefficient of our polynomial, we see that it is a 8. And so what I kind of recommend, first of all, is to, uh, for 8, just try factoring out. So it can be a multiple of 2 times 4. It can also be a multiple of 1 times 8. And so just what I recommend is trying each of these values as the constant of division for our interest. And so it can be either positive or negative, uh, but that we'll have to do by trial and error. And so if I kind of try, let's say we did +4. It is a kind of divisor of 8. So if we tried +4, then we drop down 1, we get 4, we get 2, we get 8, we get 2 again, and then we multiply 8 again, by 4 again to get 8. And then after we add, finally we get a remainder of 0. And so, uh, like I just did, sometimes it might take multiple tries to kind of get the correct answer. In that case, uh, worry not, just calmly try each po case possible, and always just try a divisor of the last coefficient, or also known as the constant. And so once you do each of those values, one of them will be a correct value. And so we found out that we can divide the third degree polynomial into. And so another thing is this will be our remaining second degree polynomial, or the polynomial 1 degree below. And so it'll be a second degree. And these values, these number values are just the constant, or just the coefficients of each variable, and so, or of each degree. And so we just write them down as they are, as such. And so we factored this function into this form. And so from here, you can try factoring this also, but just to save time for our explanations, I'll kind of tell you that there are no further factoring that is possible for the this quadratic function. And so we got a solution of x equals 4 that works. And so we know that D is a correct solution. And so we can cross out D from being a incorrect solution. And so from here, we'll check also. Let me see. Yeah, we'll now check the remaining part of our polynomials, or the other quadratic function. If we were to do that, let me just erase this top part here. One moment. Yeah. And so you can just try factoring with just trial and error, or you can just use the quadratics formula. And so if we just use the quadratic formula, then we get a value of, excuse me, yeah, so we get a x value of -b, which will be -3, plus minus b squared, which is 3 squared, 9, minus 4ac. And so we get -4 times 2 times -9. If we're to just multiply everything, we'll get a +72. and that will be over just a, which will be 2 for our case. And so if we simplify this expression again, we get negative 3 plus minus, the root will be equal to negative, excuse me, just plus minus root 81. And if you remember, root 81 is just 9. And so we'll write 9 in place of our simplified root. And so that'll be 2 on the denominator. If we were to do this, solve through, that we'll get two values, one for plus and one for minus. And so if it was plus 9, then we will get a value of positive 3. If it was negative 9, we will get a value of negative 6. And so if we do this, then yeah, so this will be the two answers that will work. And so x equals 3 and x equals negative 6. And so uh, excuse me one moment. Let me just check the solution and hmm. Okay, I think there might be a mistake in the question. So it will be covering which is a correct solution, not a correct solution. Excuse me. Seems to be a lot more errors than I thought in this today's class. Excuse me for that. Kind of rushed through trying to make this and balancing my schedule. But no worries. So if we take a look at the corrected question, then we can see that we got solutions of x equals 4, 3, and negative 6. And so from here, if we choose a correct solution, we uh, then we get a answer of D, or positive 4. And so, because every other answer choice is not a answer choice that we found or a correct solution that we found through factoring and the through factoring, and so our final answer will be D if we were to do which of the following is a correct solution. Excuse me for that. Does anybody have any questions? Okay, seems like not, and so we will be moving on. Okay. Yeah, I'll fix this question up. There might be an error with that one. Uh, and so moving on to our next concept. And so every other concept from here will be basically similar to what we just did. And so factoring polynomials is meaning the factoring expresses a polynomial as a product of simpler polynomials. And so just what we did. And so key skills is to practice factoring quadratics, differences of squares, as well as grouping. So we'll take a look at what that all means through our example questions. And so our example question states, function fx is expressed as follows. What is the y-intercept of fx minus 5 when fx is equal to x plus 12 times 2x minus 5 times 3x minus 4? And so, okay. Yeah. And so we're asked to find a new y-intercept when we have a function fx minus 5. So we added a minus 5 to our original fx polynomial function. And so if we do this, we usually call this shifting the entire the graph uh, in terms of the y plane. And so the reason we say we shifted it in the y direction is because if we add a constant or any other numerical value to the end of a polynomial function, we basically, so for example, if we had a third degree polynomial that looked like this, if we added a minus 5 to it, we actually quote unquote, shifted it because it was negative 5 downwards by a magnitude of 5 so that we get a new polynomial that looks something like this. And so we'll take a look at why this might be. And so if we just try to solve it, then we can write down fx minus 5 as x plus 2 times 2x minus 5 times 3x minus 4. And so, and at the end, we add a minus 5 because we added a minus 5 to this part here. And so from here, uh, okay, so we had to, with this entire kind of expression of a polynomial and minus 5, we can write it as an entirely new polynomial. So for example, it can be anything. We just write it down as gx for now. And so now we have to find the y-intercept of this new gx function. And so if you remember, the y-intercept is when the x value is equal to 0. And so for gx, we'll replace x with 0. We'll plug in 0 for its value. And so from here, we just plug in 0 to this entire function here that we wrote on the right-hand side. If we were to do that, then we get positive 2 times negative 5 times negative 4, and then at the end, minus 5. So if we were to solve through this, then we get a value of negative 10 plus 40 minus 5, which will equal to positive 35. And so our answer will be choice C, or 35. And so if we actually kind of go back and check the y-intercept of just fx, not gx, then it is equal to positive 40. And so we can see that by adding a negative 5 to the end of our fx polynomial, we shifted down the y-intercept by a magnitude of 5 from positive 40 to positive 35. And so, kind of like I explained in the beginning, if we were to have a polynomial like this, and for our case, our original y-intercept was positive 40. But then because of the negative 5 that we added, or the numerical value we added outside or at the end of the original polynomial, we shifted it in the y direction into so that we got a y-intercept of positive 35. And so just a key thing to remember for this case, this problem kind of talked about shifting within the y direction. And so kind of just important tips and graphical concepts to memorize. And so does anybody have any questions regarding this question? Okay, it seems like not. And so we can move on. Yeah, solution is as is, and the tip is to find the y-intercept, substitute x equals 0 into the factor form, and multiply the constants carefully. And so, like we just did, always remember y-intercept is when x value is equal to 0. Okay, this time we'll take another look at a practice question. And so the problem states the following function f of x has a y-intercept of negative 78. If b and c are both integers, what is the largest possible value of b plus c? Okay. Oh, excuse me. Okay, so we are given a polynomial f of x where we don't know two of the numerical values, b and c, but we do know that the y-intercept is a value of negative 78, and that both b and c are both integers. And so, with just knowing the information of what the value of y-intercept is, we'll plug in x equals 0 into the polynomial to kind of get a grasp of what this function kind of expresses the y-intercept as. And so if we're to do this, very simple, we plug in x equals 0 so that we get 3 times b times c. And so if we multiply that, that's just 3bc. But then we have to remember that this is equal to the y-intercept that we're given of negative 78. And therefore, b times c it will be equal to negative 78 divided by 3, or negative 26. And so we found that b times c is equal to negative 26. And we also know that b and c are both integers. Very important. And so we have to find the largest possible value of b plus c. And so here, there's no more other hints regarding what BNC is, but this is enough information to find a maximum possible value of B plus C, because if we know that B and C are both integers, excuse me, then we can just kind of uh, find every possible value that B and C could be. And so if, for example, if B was 1, then C will be 26. And just remember that we're only looking at the magnitude for now. There is a negative sign, and so the two numbers will have different signs or opposite signs. But for now, we're just finding what we can divide them into. And so if B was equal to 2, then C could also be 13. And then the opposite could be 3. It can be 13 times 2. It can also be 26 times 1. And so from here, every possible value, I guess we can kind of write down. So if we have a table of values of B and C, if B was positive 1, C will be negative 26. If B was positive 2, C will be negative 13. Uh, Again, if B was 13, then C will be negative 2. If B was positive 26, C will be negative 1. And then the other way around is also true. If every value of B was negative and every value of C was positive, that would also be a correct solution. And so from here, we have to find what is the largest possible value. And so I'll also write down continued as such. It would also be negative for all of B and then positive for all of C. But from here, we can see that we have a maximum value. So we just have to add each value. So if we add these two, we get negative 25, which is pretty low. If we add these two, we get negative 11, which is still kind of low. If we add these two, we get positive 11. So we got our first positive value. But then our last possible addition, 26 plus minus 1, we get positive 25, which is our theoretical largest value of B plus C. And also the other way around, it's the same values that we get. And so our final answer for what is the largest possible value of B plus C would be 26 minus 1 or equals to positive 25. So our final answer will be positive 25. Any questions regarding this problem? Okay, seems like not. That's great that everybody understood.
Hello?
Yes. Oh, excuse me.
Can you hear me, sir?
Yes, I can hear you.
I just fixed my mic and I found that there was a hole in there. That's why my voice was not being heard by you.
Okay, I see. It wasn't plugged in all the way. Okay, no worries. Now that it's fixed, I can hear you very clearly, and so that's great. And so, yeah, coming back to the question, so 25 was the answer. I'll fix all the solutions. There seems to be some kind of error regarding them. But then if we go through, our next concept will be finding roots of polynomials. And so again, kind of the same thing that we did. And so there's not much to kind of cover, but just remember how to do just factoring as well as utilizing the irrational root theorem to factor, like we did for previous questions. And so I think we can just go right into example questions for now. And so the problem states, according to the function f of x displayed on the xy plane below, what is the sum of all solutions that are integers from the function f of x plus 4 equals 0? And so this time, we also kind of shifted f of x using a numerical value, but then this time it's inside the parentheses of f of x. And so what this means is that if you remember our previous question, if we added a numerical value outside, so a negative 4, for example, then it was shifting in the y direction. But then if there's a numerical value that's added inside the parentheses of a some kind of function, then that's shifting in the x-axis. And so we're shifting the entire graph to the right or to the left. And so so key things to note is that, for example, if we had our original kind of function of f of x, for example, and then we can say that f of 0 was equal to 0 because for our example situation and our example f of x, it passed through this inside the origin. But then let's say, for example, we got another graph, but this time for the function f of x uh, plus 4. If we're to get this value, then this new graph will be shifting the entire fx original graph to the left by a magnitude of 4. And so it will look something similar to this. And so the reason we say even if it's a positive value inside, that we shifted it to the left by, so we shifted it by negative 4, is that if you check when f of x is 0, then we get a value here. But then more importantly, when we check that f of uh, if we replace x with negative 4, so when x is equal to negative 4, then we get f of 0 for the new shifted function. And so we shifted this point where x was equal to 0 to the left by 4. So that when x is equal to negative 0, that's when we get our y value of 0. And so it's important to realize the difference in kind of the notation when shifting in the x-axis or the y-axis. When you're shifting in the y-axis, you have a numerical value, let's say, for example, just 5. If we add positive 5, then you shift it upwards. So you add positive 5 to the entire function's y values. And then if you added negative 5, on the other hand, you decrease or shift it downwards by 5. But then the opposite notation is true for shifting in the x direction. And so if you shifted it in the positive 5 by positive 5 or x plus 5, then we shift it to the left by a magnitude of 5. Or you can also think of it as decreasing the x value of each point by negative 5. The opposite, and then for the other way around, if there's a f of x minus 5, then we shifted it to the right by 5. And so we increased it by 5. So don't get confused for especially the x-axis shifting, just because it is a negative value on the right next to the numerical value. It's not shifting to the left, it's actually shifting to the right. So we're increasing when it's negative and decreasing when it's positive. Uh, a reason for that is because when it's negative 5, at x equals 5, it will be the same value as when it's x equals 1 before shifting. And so that's why we say it's shifted to the right, even though our notation is in negative 5. And so just key things to remember before we move on. And so anybody have any questions regarding this concept before we move on to our problem? Okay, it seems like not, which is great. And so we'll go through our question now. And so the problem states, yeah. And so like we kind of covered, so we have f of x, the original f of x before it's shifted in the x-axis as shown. And then we need to find what is the sum of all solutions that are integers from the function of this new shifted uh, f of x function. And so we can see that is instead of x is x plus 4, which means that the entire graph shifted to the left by a magnitude of 4. And so how we can utilize this information is that first we find the roots of every root. So let's say if there was 3 roots for the original fx before it was shifted. From here, in order to find the roots of f of x plus 4, we just minus each root by 4 because everything shifted to the left, so each root will also decrease by a value of magnitude of 4. And therefore, we just have to find these values. And these will be our answers. And so if we were to find the original roots of just f of x beforehand, you can kind of check the graph. I'm not sure how it will show up if it's large enough, but then we have our first integer solution at x equals negative 3 here. And we have another solution at x equals 2 here, positive 2. Then we have another solution that's at this point, but it is not a integer value because it doesn't cross at any of the points where x is a integer. And so the only integer solutions will be when x is equal to -3 and also +2. But then this is only for our original f of x function. Now we need to find the solution of our new shifted f of x function, which will be, let's say it's just x prime, for example. Then the solution for that is just these solutions, but we decrease them by a magnitude of 4 so that we get -7 and -2. And so uh, we know these two new solutions of the shifted function. And so we need to find the sum of these two. And so if we add these two up, we get a value of -9, which will be our final answer. And so anybody have any questions regarding this problem?
Um, sorry, but the third point,
Yes. Mm.
I don't know, but it kind of looks like a 7.5 or
Okay.
is it
Uh,
just me? I don't know.
yes, that is true. The third point here is around roughly 7.5. But then the reason we don't include that point is because the problem asks for, uh, if you read here, what is the sum of all solutions that are integers from the function
Oh,
here? So we only care about integer solutions.
okay, thanks.
Yeah, no worries. And so if we got that out of the way, any more questions? Uh, Seems like not, and so we will move on. And so solution is as is, and a tip is to when shifting a function like f of x plus 2, subtract 4 from each root to account for the horizontal shift. And so I think this was a great example for now that we covered both shifting in the x and y axes. I hope you guys are kind of more familiar with it. And so just looking at the kind of time, let me just go through kind of the questions we could see. Okay, I think we can do these two final questions and then we'll call it a day for today. And so I've kind of previous concept, it wasn't too important, and so I'll be skipping it. But then this concept for graphs of polynomial functions, I think is worthwhile covering. And so the definition is that graphs show roots, intercepts, and end behavior. End behavior meaning kind of if we have a graph as such, which kind of the direction the ends of the graph point. It could be for this case, it was a third degree. It could also be for second degree. And so graphs tell us a lot of kind of very important information regarding the actual algebra of their functions. And so it's important to know how to analyze them. And so key skills is regarding finding roots or the x-intercepts, as well as the y-intercept, and also some turning points. And so we'll take a look at an example question going through this concept. And so the problem states the following polynomial function f of x equals ax to the power of 3 plus bx squared plus cx plus d and is drawn on the xy plane below. Which of the following statements is true? And so we need to find a true statement after looking at this graph. And so let's just read the first statement. So the statement one says the sum of the solutions of f of x is positive. Okay, so we need to first sum the solutions of f of x. And we have to check if they are positive. And so if you take a look at the graph and look at the x-intercepts, uh, we just need to find kind of the general values of each solution. So if we're to do that, the first point will be slightly below -5. So let's say it's somewhere around 5.1, for example. And then our second point is basically on x equals -2. And so our second solution we can kind of say will be -2. And then our third solution or third point here is between 3 and 4. So let's say, for example, it's around 3.5. And so if we add each of these solutions up, then the sum will equal, uh, so it'll be negative 7.1 plus 3.5, which would then we will get negative 3.6 as our sum. Uh, the actual exact value might be different, but then the general ballpark is still much in the negative area. And so that's why we can say the sum of the solutions will be negative, not positive. And therefore, statement one will be incorrect. Uh, any questions before we move on to other statements? Okay, seems like not. So we'll move on to statement two. So statement two says A times D is a negative value. And so we can see that A is our coefficient of for x to the power of 3, and D is our constant. And so the easier of the two to find will be the value of D, or the constant, because the constant in a polynomial represents always the y-intercept. And the reason behind that is if we plug in x equals 0 to our fx function, then we get fx equals, excuse me, oh, oh, why is it not writing for me? Okay, oh, one moment. Seems to be something slightly wrong. Okay. Why is it like this? Sorry, excuse me, technical difficulties. Seems like my pen is not writing for some reason right now. Let me just exit full screen and then re-enter. Okay, it seems like there's something wrong with uh yeah, oh, why is my mouse being like this at a time like now? Excuse me for that. Let me just clear up the screen for now. Uh, hmm. Yeah. Sorry, there's something wrong with my touchpad right now that is not allowing me to do so. Let me just stop screen share just briefly and I'll try to sort it out. How is like this? Okay, I think I got it working. Sorry about that. Uh, I'll go straight right into as we were. Okay, yep. Can everybody see the screen correct?
I can see the screen clearly, sir.
Okay, thank you. Yeah, fixed it. Sorry about that. And so coming back to our second statement here, A times D is a negative value. We can say that D is the y-intercept, and it's because when we plug in x equals 0, then we get a value of just positive D, because every x value will become a 0, and the only thing that remains will be D. And so this will be our y-intercept. And so knowing that these are y-intercept, we can just check what the y-intercept is on our graph, which is at this point when y is equal to positive 2. And so we can say that d is equal to positive 2. The exact value isn't necessary because we just need to care about the sign. And so we know that d is positive, then that means a has to be negative, but then we have to check And the so how we can check what the sign of the coefficient of x to the power 3 is by checking the end behavior, like I talked about. And so if you look at the graph itself, we can see that on the left side, the end curves upwards, and on the right side, the end curves downwards. And so we can kind of check this out and say, okay, let's say if x keeps on increasing, then the graph will keep on decreasing into the negative value. This means that a would have to be, so if we again write down f of x in a one line, x to the power 3 plus b to the x to the power of 2 plus cx plus d. Uh, Key thing to note is that as the x value magnitudes gets greater and greater, the value of a to the x power of 3 will get much larger compared to the other values here. And so if we get a large enough x value, let's say close to infinity or like 100,000 or 1 million, then this value will be overpowering, will be kind of deciding what the sign or the kind of general value will be for the y values. And so we can see that when x is increasing in the positive this direction, it keeps on decreasing into the negative area, which means that a would have to be negative. Because once a is negative, when we increase x, then let's say even if we have just x to the power 10 to the power of 3. So if we say x is equal to 10 and a was equal to negative 1, then it will be negative 10 to the power of 3, which is already negative 1,000, which is much larger than any of the other values that we can get from here. And so it kind of the sign of the coefficient of the largest degree kind of decides the direction of the ends and the tails of the graph. And therefore, knowing that, we can say that a will be a negative value. And we're not sure what the exact value will be, but we only know that the sign will always be negative. And so knowing this, so a is negative and d is positive. If we multiply those two, then we get another negative value, which proves that statement 2 is a correct statement. Any questions before we move on to statement 3?
Not any, sir.
Okay, that's great. We'll move on to statement 3 now. And so statement 3 talks about there are two values of constant c where there can be two intersection points between the graph f of x and the line y equals c. Okay, so this is an interesting statement. And so we're kind of asked to say, kind of prove if there are two values of constant c where there can be two intersection points. And so if you take a look at the line y equals c is just a horizontal line because the y value is always constant. And so we have to find values of c where we get uh, two intersection points. And so, for example, if we draw an example line that goes through, let's say, so this line represents y equals 2, or y equals positive 2 for our case. You can see that there are intersection points at first one here, second one here, and then a third one here. And so we don't want three intersection points, we only want two. And so we have to think, okay, what other point or what other line will only get us 2 points? And so these end tails, no matter what, how small or how large the value of c is, we always cross these. And so we only need one more extra point. That comes at these direction changing points. And so if we focus on these direction changing points where the direction changes from decreasing to increasing or from increasing to decreasing. And then if we have a line that goes through that point, for example, one like here and another one like, oh, excuse me, and another one just between the 2 and 3, like here, then we can see that, yes, there are values of C where there will be only 2 points of intersection. And so you can kind of check that. So for the top, the line above, the two intersection points will be one here on the left side, one on the direction changing point. For the line below, one on the left side, left hand direction changing point, and on the other tail end of the graph. And so uh, yes, there are two values of the constant C where there can be two intersection points. And so the exact values of C will be -1 and roughly around between 2 and 3. So let's say we could say 2.5. But then the exact values aren't important. It's just we know that there are only 2 points. And so the only true statements are statement 2 and statement 3. Before we move on, any questions? Okay, seems like
Not at all, sir.
So C is a constant.
uh, yes, C is a constant.
Yeah, but like, how do we know though? Like, what's the reasoning behind it?
Okay, yeah, we can go through that. And so the statement says that there are two values of constant C where there can be two intersection points. And the reason we say C is a constant is because if we take a look at this equation, y equals C, and if the question gives us the kind of requirement that C is a constant, then this line, y equals C, when C is a constant, will just be a straight line that is horizontal. And so uh, if, for example, the line that we have to think about was not a constant but a linear line, then it will be different. But because C is said to be constant, we just say it as a horizontal line.
Okay, so it depends on the question.
Yes, and what the statement kind of tells you that the C will be.
Okay.
Yeah, no worries. And so that will bring us to, yep, solution is as is. To our final question, the challenge question of today. And so quickly going through, the problem states the cubic function f of x is expressed as fx equals x to the power of 3 plus bx squared plus cx plus d. If the y-intercept of f of x is 0, comma 40, and the solutions to this function are -2, 4, and a variable a, or unknown value a, where a is a constant, what is a value of a minus b plus c minus d? And so this question kind of requires us to uh, have another kind of concept or idea that to know. And so if we covered those beforehand, and so we have a polynomial to the degree of 3, which means we have to multiply. If we were to factor, there will be 3 linear equations. And the coefficient of each x value is just 1 because the coefficient of the greatest degree is also 1. And so from here, we know that the solutions of the functions, or before we do that, let's say this, ignoring, okay, what variables can we use? Let's say our roots are as such. Okay. So for example, if our roots that we already knew were alpha, beta, and gamma as such, then we can write the factor or the factored version of the polynomial as such, like we did here. And so if we were to just solve through this, then we would get the expression alpha beta times beta uh, theta, not theta, gamma, excuse me, plus gamma alpha x squared plus minus alpha minus beta minus gamma x, and at the very end plus, uh, or not plus, but minus uh, each root multiplied to each other. And so if you memorize this kind of function format and this kind of way is organized when we solve through, then we can see that the coefficient of x to the power of 3 isn't really important, but every other coefficient is. So if you take a look at the coefficient of x to the power of 2, then they are the sum of multiples of our solutions. And so if we have three solutions or three x-intercepts, then if we pair two different distinct values to each other, uh, have a product of them, we multiply them, and then we add them up, we get the coefficient of x to the power of 2. And then for coefficient of x, it's just the negative addition of each of our roots that we know. And then the constant will be the negative sum or the negative product of every uh, root that we know or solution that we know. So knowing this information, we can kind of say that when we're given the polynomial in the problem as such, then b would equal, as you can see, we'll just do this exactly as it is. And so we multiply by choosing two of our solutions, distinct two solutions. And so what I like to do, if we know that the solutions are these values, these three values, -2, 4, and 8, I first pair the first two up, so we get -2 and 4. So that if we multiply -2 and 4, we get -8. Or I guess we can just write -2 times 4. And then we also add, after we did those two, we can now do, keep the first one, but then we move one to the right for the second value. So we multiply -2 and a, so that we get -2 times a. And then our final possible product will be multiplying 4 and a together, so that we get a value of 4 times a. And so if we were to do this and solve through, then we will get a value of 2a minus 8. And so this way we can re-express the variable b as a expression that involves a variable only a. And so this will be a key thing to that we'll be going through. And so we'll just keep on finding re-expressions of b, c, and d in terms of a and other constants. Okay, so I'll write down what b is here, right here. And then now we'll try to find a value of c. And so if we try to find the value of c, then we can see that c is just the sum of the negative solutions. And so we just add a negative in front, and we just add each of our solutions that we know. And so if we, after we do this, then we get a c value of -a, -2. If I am correct, yes, okay. Yeah. And so if we do this, then we get c is equal to -a, -2. And so final value that we have to find is for the value of d. And so for d, we can see that it is the negative product of each solution that we know. And so we can write that down. And so if we take a look at our solutions once again, that's written here. We just multiply everything so that we get a value of -8a. But then important thing to note is that, like I said, the constant or the final constant value of a polynomial is always the y-intercept. And so if we're to do that, then we also know that the y-intercept value is +40. And so we can say that this is also equal to just 40. Excuse me. Oh, excuse me. We have to add a negative in front because it was a negative product. Yeah, excuse me for that. And so if we do that, then we will get, it was +8a, excuse me. And so we can also write that d is equal to 8a, but then that's also equal to 40, which means that we can say that a is equal to 5. And so this a equals to 5 we'll use a bit later. We won't use it right away. And so knowing all this information that we know now, we can actually solve for our final value that we have to find, a minus b plus c minus d. If we're to do that, then we'll keep a as it is. We'll change b into -2a minus 8. We'll add c so as to get -a, -2. Then we add negative d, which will be -8a. And so if we simplify this by adding like variables to each other, then we get, this will become -2a plus 8. This will become -a plus -2. This will stay as -8a. So if we're to do this, then we'll get -10a. Uh, excuse me. Yes. Okay. Yeah. And so we'll get minus 10a plus 6. Excuse me, there might be slight error. No, I think it is correct. And so if we go through and we plug in now, a is equal to positive 5, then we get the value of, uh, excuse me, yeah, okay, negative 50 plus 6, or a value of negative 44. Uh, I was just slightly confused because it was different to the solution that I did previously, and I'm just trying to find out where I made a mistake. Uh, Let me just check the solution I wrote previously. Our uh, b value, or the re-expression of b, was negative 2 minus 8, because the kind of solution that we did beforehand. Okay, why is this not working? Oh my goodness, okay. Yeah. Uh, I'll try to find a solution for that. So our expressions for B and C were mixed up. So it's the other way around. That is correct. If we're to do that, then we just follow the same steps that we did before. But then the written solution that is written here has to write re-expressions of B and C. And so if we plug each B, C, and D and their re-expressions into A minus B plus C minus D, then we get another expression in which we can replace a equals 5 like we found previously, so that we get a final answer of negative 26. And so any questions before for this question?
Also,
Okay, I think then that will be all for today. Uh, Small technical errors, excuse me for that. And so yeah, that will be all for today's class.